Hello there, welcome to another presentation on solving differential equations using the method of undetermined coefficients. My name is Charles Van Msipa. This is part one of handling equations which are non-homogeneous. Let's first of all start by recapping what we saw before. The introductory part of this work concerned the fact that a differential equation, first order linear differential equations of this nature, could be simplified to this kind of version where p of x is a constant m, and then in coming up to this method we are talking about, what we did actually, we started by setting the right hand side of the equation f of x equal to 0 to create an equation of, for example, of this nature: dy dx plus 2y equal to 0, which we said it was a homogeneous equation. Okay, I'll come back again to this concept of homogeneous equation. So what we then did was actually so that an equation like this would actually reduce it to a kind of an algebraic equation of this nature, which is my plus 2y equals to 0, whereby we saw that we could now factorize this and write this equation equivalently as y brackets m plus 2 equals to 0. And you say this y we're talking about here is still the same solution of this equation we're talking about there. And we said we would always assume that y is a non-trivial solution, meaning that y is not identical equals to 0. So in that case, if we've got this form, we say then we would arrive at the fact that m plus 2 is equal to 0, which we call our characteristic equation, or some people they refer to it as an auxiliary equation. So after that, we saw that if we solve this auxiliary equation, we would get that m is equals to minus 2, and thereafter we could actually construct or build the solution y function of x is equals to c, an undetermined coefficient, multiplied by e to the power of minus 2x, 2 being the root of this characteristic equation here. So then we took this equation from this, at this level, dealing with the equation of first order, and we take the equations of order 2, and we can generalize that into equation of order 3, and so on, or let's say equations of order n greater or equals to 2. So by looking at this equation, we also note that we've got the right hand side here, which is q, and we should understand that q, the right hand side of the equation, can be actually a function of any type, which could be a polynomial function, a function of this nature, or a trigonometric function. Here I just write trig of x, meaning a trigonometric function which you can express this way in general. Or f could be an exponential function which could be expressed this way as alpha e to the power a x. Or in general, this could be a combination of the above. In other words, f of x equals to 2x plus sine 2x plus 3 e to the power x plus 1. If you look at this, you can see that in 2x plus 1, we've got a linear function here when a2 up to an are equal to 0. That will be a polynomial. And then for this trigonometric function here, sine 2x, we simply have got this kind of situation whereby b will be equals to 1 and the a for cosine will be equals to 0. And then lastly plus 3, that which is an exponential function. So what I'm trying to say to you here, that given an equation like this, the f of x here, which is the side for q, can be actually be any type of function of these functions, or a combination of them, like here we're combining this function by addition. In solving this equation, we already seen that we started by considering the general form of the equation like that, and then setting f equal to 0, getting what we call a homogeneous differential equation. And a particular example of those equations which you saw before are these three equations which you've got here. Now let's talk a little bit about homogeneous equation in relation to what differential equations model, which are systems. Talking about the modeling systems, let's take the example of an RL circuit, which is the following. And we saw that the differential equation modeling this system is L di dt plus Ri equals to V, which is the voltage source here. And as it is, we've got two situations we can come up with here. It could be that in one situation, let's say case number 1, V is equals to 0. Then the differential equation will look as follows: L di dt plus Ri equals to 0. On the other hand, if V is not equal to 0, then V could be any kind of input which is represent voltage. For example, we could have L di dt plus Ri equals to, say, maybe let's say 50 sine 100 pi t, which could be an oscillating kind of voltage source. So in that case, when it's 0, and looking at a differential equation modeling an input-output system, we could say now the differential equation is the model which represents the system, and then the input normally will be considered to be the right-hand side of the equation. This is the input to the system. And then the solution here, which is actually going to be I of t, will be the output of the system. So when you see the differential equation with a 0 on the right hand side, it means the input to the system model is equal to 0. And when it's non-zero, so it will be actually, there will be an input which is actually exciting the system, and then obviously the output is going to change accordingly. So in this case, where the right hand side is equal to 0, that's when we talk of a differential equation being homogeneous. And then the opposite is non-homogeneous. Now, going back a little bit, what we saw actually in the previous example was to solve homogeneous equations. So let's start by recapping on the first case which we saw. Like, for example, we had a differential equation of this nature. So in solving this differential equation, what did you do? Let's say we set up a solution. We firstly determine the characteristic equation of this differential equation, which came up as m squared plus 5m plus 6 equals to 0. And in this case, factorizing, we saw that this was going to be m plus 2 multiplied by m plus 3 equal to 0. And solving, this is simple, giving us the fact that m is equal to minus 2 or m is equal to minus 3. Then from there, we then build our general solution, which is xg of t, because this is a function dependent on t, which is equal to an undetermined coefficient, let's say the initial one, c, e to the power minus 3t, plus c1, e to the power minus 2t. In this case, what's important here, you must see here that we arrived at the roots, two different roots, which are actually real roots. Now it's minus 2 and minus 3 are real numbers, and minus 2 is not equal to minus 3. Now we've got two different roots, and then we obtain the solution using the roots this way. Then the second case was the following, whereby we've got a differential equation of this nature, and getting the solution here, we started by again setting up the characteristic equation, which is m squared minus 6m plus 9 equal to 0, and that this factorizing gave us m plus 3 equals to 2, m plus 3 to the power 2 equal to 0, which actually means that the factor m plus 3 is repeated. Since it's repeated, in this case twice because of this power, we then say here m is equal to minus 3 twice. What we see here, we see that minus 3 is actually a real root, but most important, it is repeated twice. So then we saw that in this case we would get a solution which would write this way and say xg, which is general solution, which is equal to the initial undetermined coefficient, they say C0, e to the power minus 3t plus C1 t e to the power minus 3t, which we simplified and wrote as C0 plus C1t multiplied by e to the power minus 3t. So then there we learned how we would handle repeated solutions, repeated roots of the characteristic equation. And the third case, which is, and also the final case, is the case which we had equation like this, and then setting up our characteristic equation or auxiliary equation, we'll get m squared plus 2m plus 5 equals to 0. And we'll notice that immediately this equation we cannot factorize, then we apply the formula whereby we get m1, 2, which is going to be using the quadratic formula, which is going to be minus 2 plus minus square root of 2 squared minus 4ac, which in this case our a is 1 and the c is 5, all over 2. And that's simplifying that, this takes us to minus 2 plus minus square root of minus 16 all over 2. Going further, we get minus 2 plus minus square root of I squared by 4 squared all over 2, which later this simplifies to minus 1 plus 2i. So in this case here, which means we've got an m which is a complex quantity, which is a plus b I plus or minus. So what we notice here that we simply ignore this and focus on a and the b, and then when you're going to write your general solution here now, this will be x g of t. Then we take these numbers as follows. You get a e to the power little a t cosine b t plus b, now the next undetermined coefficient, e to the power a t sine b t. In this case, if we now look at this, we are simply looking at this being equal to minus 1 plus or minus 2i, which simply tells us that a is equal to minus 1 and the b is equal to 2. So our solution is going to look like the following. We can see that this e to the power at is a common factor, so we're going to write this as a cos 2t plus b sine 2t in brackets multiplied by e to the power minus at, a being minus 1, so minus that. this is what we saw. In this case, we've checked all the three cases. In other words, we've got different roots, which is case 1. We get the solution this way. Then when we've got repeated roots, we've got that. And the final one, we've got complex roots, we do the following. Going forward, we're going to need all what we've seen, what we've recapped in this session here. So now we proceed to deal with equations which are non-homogeneous, which is our focus today. So looking at equations which are non-homogeneous, we would solve an example of this nature. We've got dy dx second derivative plus 3 dy dx plus 2y equals to f of x. Now you see that f of x there plays the role of q in our linear equation. In this case, we're considering when f is not equal to 0, then we talk of a non-homogeneous differential equation. Now let's start by looking at this as a homogeneous equation. I think from what we've seen before, you know what to do. You can proceed and basically repeat or recap, do it yourself, and see that you get the right solution here. So let's proceed to a non-homogeneous equation, and the simplest one in this case, whereby this is a constant. In other words, if you recall your polynomial function, which was like this, it simply tells that a1, a2 up to an are 0, and then this independent term a0, which is a constant, is our 5 in the equation here. That's what we have there. So basically we've got a polynomial of order 0. So to solve this, let's start by stating solution. What we do, we'll do this in two parts. We'll handle this as if we are solving a homogeneous equation by simply saying, first, let's say part 1 here. We'll simply set this equation to be homogeneous, meaning we ignore 5 momentarily. In this case, we take dy2 dx2 plus 3 dy dx plus 2y equals to 0. Now, I hope you understood what I said. So you take this non-homogeneous equation and momentarily you treat it as if it is a homogeneous equation, and you actually solve it. Then when now solving this, you set up your characteristic equation as m squared plus 3m plus 2 equals to 0. Then factorizing here, I hope you can see that you are going to get m plus 1 multiplied by m plus 2 equals to 0. Then you simply conclude here that your m is equal to minus 2 or m is equal to minus 1. Now here you would proceed like we saw before and get a solution. In this case, this solution, we're not going to label it y general, we're going to label it yc, meaning y complementary solution. Complementary. So then you write here your y of x, which is yc, which in this case you write your first undetermined coefficient c0, e to the power minus 2x plus c1, e to the power minus 1x, which will be your complementary solution. That's the first part of solving this equation. Then the second part, you do the following. You now want to find another solution. In other words, I'm going to write here determining a particular integral. Remember we said before that when you're solving a differential equation, we could actually talk of integrating a differential equation. So a solution to a differential equation can also be called the integral for that differential equation. So determining a particular integral. Already what I'm implying here is that to solve this equation consists in determining what we've called a complementary solution and also determine what we call a particular integral or a particular solution. Now we need to now go very slowly over this. First of all, if you look at the differential equation as it is here, this 5 we said is the input, and the solution y which we're looking for is the output. So in this case, there's a solution y which we're looking for here, but actually it's going to come up from the complementary solution, which in this case is going to be y c plus what we're going to determine now here, which is called particular integral, which I'm going to write here as y pi for particular integral. So which means the solution to this equation is actually a sum of 2. And I hope you still remember that if you've got a solution to differential equation or two solutions to differential equation, the sum of the two is still a solution to a differential equation. You can actually verify that this is a solution to that differential equation, the homogeneous solution equation, and it's also then if you find the particular integral, you just simply need to add the particular integral to make up the solution for the non-homogeneous case. So now, coming to the case of the particular solution, let's think this way. Modeling a system, we said with system here, there's an input, there's an output. So if we put an input here, obviously the output would be a kind of the input after being transformed by the system, then it gives us output. So now we expect that if we input a constant here, let's say like 5, so obviously this 5 is going to undergo the transformation which the system does and give us an output here, which actually in this case we don't know. But because this input here is a constant function, we should expect that the output is going to be out here, which is going to be given out here, is also going to be a constant, but a constant which results from the action of the system on a constant 5. Then that let us make us suspect that the particular integral y p I should be some constant, let's say alpha. My argument is that if I input a constant to a system, the system is going to transform the constant which I put and actually give out a result here, which has got some characteristics of the input which I put here. Like for example, if you put into a system some grains of millis, what I'm going to get here, you might get some powder like millimil, but that powder millimil, it really has got some, is a kind of a version of transformed grains of maize seeds. So this is what I'm saying here, that I would suspect that if the input here is a constant, the output will be some kind of transformed constant, and let's say that transformed constant is alpha. Now what the claim is that this alpha is a solution, because the output, we say the output is the solution. So if that is the case, if this is the solution, this particular integral must satisfy this non-homogeneous equation. By satisfying, what do I mean? I mean that if I plug alpha here and plug alpha there and differentiate once and drive after there and get the second, this equation must balance. So what do you mean there? This is what we're going to do. We're going to say d2 alpha dx squared plus 3 d of alpha dx plus 2 alpha. This must be equal to 5. This equation must balance. Reason why? Because we're claiming that y pi equals to alpha is a solution. A solution must satisfy the equation which is claimed to be the solution of. So this is what we've got here. So proceeding here, what we do, we would differentiate alpha with respect to x, but alpha is a constant. Like I suggested, that if I input a constant, I'm expecting to get a constant which is somehow transformed by the system. So if I differentiate alpha as a constant, I'll get here 3 times 0. And the differentiating, the second derivative of alpha is actually derivative of 0, which is going to give us 0 because 0 is a constant. And then plus 2 alpha, that will be equals to 5. Now simplifying this equation, you can see that this simply gives us 2 alpha equals to 5, which then tells us that alpha is equals to 5 over 2. As you can see now, this output alpha here is actually equal half of 5, which actually means that the system, what it has done, it actually outputs an output which is a scaled 5 scaled by half. So in that case, now what I was saying is simply saying that the particular integral of the given equation is simply 5 over 2. Now what do we have now? We've got two solutions. The particular integral, which is this one, and the complementary function, which we got as C0 e to the power minus 2t plus C1 e to the power minus, no, sorry, I'm using t here, that's a mistake. So now what we've got here is the particular solution, which is ypi equals to 5 over 2, and above here we've got a complementary solution, which is yc equal to C0 e to the power minus 2x plus C1 e to the power minus x squared. So I hope you've observed what has happened here. We set up the equation to homogeneous, we obtained the complementary solution, which is this one. And then we assumed that, let's say, the input to the system was a constant. So given that the input to the system was a constant, we then assume that the output is some constant alpha, which we expect to be kind of a transformed input. So then we're getting here that the actual alpha, which is the output, is actually half what the input was. So now, to determine now, which is the third part of this stage of this work, we now need to determine what we call the general solution to the differential equation given, which we're going now to write as y general, which is simply equals to y complementary plus y particular integral, which is going to come here up here as C0 e to the power minus 2x plus C1 e to the power minus x plus 5 divided by 2. Then in this case, we have addressed the case when we've got a non-homogeneous equation and the input is a constant. Given the example which I've given you above, that example is not essentially different from any of the exercises you see in front of you here. So the purpose of these exercises, they might look easy, but the purpose of that is that you consolidate what you have seen there and learn, really do it yourself. The first step to this is actually try to repeat what I've done in the previous example. Repeat without looking at the example. Then after that, try to do each one of these exercises. And if you can do the five of them, I'm guarantee that you can do any of the similar exercises as long as you can factorize or use the formula for quadratic equation, because I picked only second order differential equation. So now let's proceed to the next example. Our next example consists in looking at a non-homogeneous equation, but in this case here, you can see that the right hand side, which is our input here, is a linear function. In this case, we are looking at the polynomial function whereby a2 up to an are equal to 0, and we're left with a1 and a0, which in this case, we're talking about a0 being 9 and a1 being 3. So now let's see how we're going to solve this equation. Solution. Again, the first step will be ignore the right hand side, set this equation as a homogeneous equation. Then we've got d2x dt2 plus 2 dx dt plus x equals to 0. That is a homogeneous equation. I'll write just here homo eqn for equation. So then after that, we do exactly what we are expected to do, which is setting up a characteristic equation which is going to be m squared plus 2m plus 1 equals to 0. Then solving this, we see that we get here m plus 1 all squared equals to 0. As you can see here, we're getting repeated roots, and we've actually recently recapped what we do when we have repeated roots. So our complementary solution here, which we write yc, is simply going to be our initially undetermined coefficient c0, e to the power minus t, because actually I've omitted one step here, which here you should have concluded that here m is equal to minus 1 twice. And then writing this solution like this, then the next term will be c1t e to the power minus t. If you've forgotten this, you better please go to the very second presentation on this work to recap this kind of work, because here I'm not focusing on this, I'm focusing on non-homogeneous equation. So now this is your complementary solution. Whilst you're doing this thing, you must never lose sight of the fact that you are actually leading to what we call a general solution, which is always going to be equals to y, the complementary solution, plus y, the particular integral. Now, having done this, we've done half of the work. Then stage number 2 of this work will be, again, looking at that system, kind of analyzing that kind of system. What we have here, the input, and we've got there the output. Now, if you look at the differential equation here, the input is a linear function. So which means the input here should be 3t plus 9. Obviously, if you input a system which sort of differentiates what is input into it, so what we're going to get here is some kind of I'll just use t here, some kind of transformed 3t plus 9. That's what we should expect. So because of that reason, that we expect the output to be some kind of transform this, then we would say the output, which you write as y particular integral, should be equals to some linear function of the same nature. In this case, I'm going to write this as alpha t plus some beta. I could have said a0 plus a1t. The constant, it doesn't matter what we use. So then, as I suggest this to be a particular integral, I'm saying this is a solution to the given equation there. So if it is a solution to the given equation there, then when I plug this function, sorry, I've used y here. Sorry, we've used y there. Let's correct something here. This is a function x, a function of t. I've used y here and there. That was my mistake. Don't repeat it. Don't repeat that mistake. So here what we've got here is xc, and then the general solution, x general solution, will be x complementary plus x particular integral in terms of t. So now what we have got here is a suggestion which you say x particular integral is of this nature. Actually, this, as we suggest this, like we suggested the alpha before, as we suggest this, we must take this as what we call a trial solution. Trial solution now, it actually serves as a kind of a model, or what you predict the solution, the particular solution, to look like, and then it actually becomes a tool to help you find the particular solution to the differential equation given. So now our next step is to plug this solution in the differential equation. Let's make that step number 3 here. So basically substituting in the equation. In this case, when I'm saying equation, I simply mean a differential equation given. We've got d2 of alpha t plus beta, second order derivative, plus 2 d alpha t plus beta, the first order derivative, plus alpha t plus beta, which is our x then, equals to 3t plus 9. So having this suggested or supposed to be a solution, we expect it to satisfy this equation. Otherwise, whatever I get here, it should be a balancing equation. So differentiating this once, we know that's going to give us alpha. So we've got here 2 multiplied by alpha, because that's a linear function, plus alpha t plus beta equals to 3t plus 9. Now, when you get the second derivative here, we'll be actually differentiating alpha, which is a constant, then that is plus 0. So what we're left with here, we're left with alpha t plus 2 alpha, alpha t plus 2 alpha plus beta equals to 3t plus 9. Now, if you look at what we've got here, we've actually got linear expressions. In other words, linear expressions, I mean, the power of t on the right-hand side is 1, and the power of t on the left-hand side is 1. And the independent term on the right-hand side is 9, and the independent term on the left-hand side is 2 alpha plus beta. If we claim these two, they are equal, there's no way they can be equal unless and until the corresponding coefficients are equal. What is the corresponding coefficient to 3? Corresponding coefficient to 3 is alpha. So we're saying 3 is equals to alpha. That's what this equation detects to us. And from there, we're saying 2 alpha plus beta is equals to 9. That's the only way these two things are equal. And what I'm using here, I'm simply using the principle of comparing coefficients. I mean, if two quadratic expressions are equal, it means the corresponding coefficients are equal, meaning the coefficient to the power 2 is equal to the coefficient to the power 2 on the other side. The coefficient to the power 1 is equal to the coefficient to the power 1 on the other side, and so on. So getting this, already you've got an answer that alpha is equal to 3. So if alpha is equal to 3, substituting here, we're getting 6 plus beta equals to 9. And if you do that, if you play around with this equation now, this final equation here, notice that alpha is substituted here to 6 and the beta is still there. You can't get anything except to conclude that beta is equals to 3. So alpha and beta are equals to 3. Then now, we can now say, therefore, our x particular integral, a function of t, is simply equals to 3t plus 3. Now, we've got a particular integral. Above, this is our complementary solution. We already know that our xg, our general solution, function of t, is going to be x complementary a function of t plus x particular integral a function of t, whereby we know now that this is c0 plus c1 t multiplied by e to the power minus t. That is taking a common factor there, e to the power of minus t, plus our particular integral now, which is 3t plus 3. Then we've got our general solution. Actually, we call this general solution because C0 and the C1 are arbitrary constants, unless if we're given initial conditions, then we could determine them. But we're not going to focus on that now. Our focus now is simple to practice the two steps of obtaining the complementary solution and the particular integral. And the most important, you must see that when the right hand side was a constant 5, the trial solution, I said let the trial solution be a constant alpha. And now in this case, when we had the right hand side being a linear function, 3t plus that, so also suggested that the trial solution xpi be some linear function alpha t plus beta. The message is, whenever the input is a certain type of function, then the trial solution must sort of be the same type of the function, then substitute accordingly in the equation and determine that. But what you can see now here, I didn't just take any constant alpha in that. I just assumed any alpha as a variable or a parameter and any beta as a parameter, and the substituting in the equation is what lends me at the values of alpha and the beta. I'm expecting to repeat what we've seen above with the following types of examples. I actually want to highlight two things here. The first equation here is got only a 9, which is actually the first type, like with 5. And this one, he has got 3t, which actually the two of these, they give you 3t plus 9. I would like you to solve these two and compare the solutions and think and see if we can conclude something from the previous example we've seen. And after that, do the two examples. And then the last example here, I'm actually challenging you from what I've said to see if you can figure out now when the input is no longer a linear function but a quadratic function. Let's summarize a bit. What we saw, the first of all, f of t or f of x, the right hand side was 5, which is a constant function, which is simple, a polynomial of order 0. And the next one, f of t, the right hand side of the equation, was 3t plus 9, which is a polynomial of order 1. And then now here, what I'm giving you an f of t, which is t squared plus 5t plus 20, which is now a second polynomial. So I've physically counted from 0, 1. I want you to continue to 2. Then from there, figure out what you're going to do when you are dealing with, let's say, t to the power 4 and so on. Otherwise, at this point, guys, I hope you have grasped what I've presented here. Thank you for listening. My name is Charles Wasfanem Sipa.